Hello everyone, and welcome. I'm excited to introduce today's presentation on green coding. We'll be exploring how to build energy-efficient applications and AI models. On this first slide, you'll see the title, Green Coding, and the subtitle, How to Build Energy-Efficient Applications and AI Models. Over the next few minutes, we'll cover key strategies and best practices to make our tech more sustainable. So, let's dive in and discover how we can make a positive impact through smarter coding. Let's start by looking at the title, Introduction to Energy Efficiency. Every line of code we write actually consumes energy. That's true whether it's a small mobile app or a large cloud service. The decisions we make in software development have a direct impact on how much power is used, on the carbon footprint, and even on how long devices last. Now, let's explore what drives this energy consumption. First, algorithm complexity plays a big role. If we use inefficient logic, it means more CPU cycles are needed to get the job done. More CPU work means more energy consumed. Next, resource usage. High memory usage, disk I/O operations, or network calls all drain power. The more resources our software uses, the more energy it requires. Then, we have idle loops and polling. Sometimes, software keeps checking for updates or events when no work actually needs to be done. That's energy waste, because the device is doing unnecessary work. Finally, cloud workloads. Large-scale models or data pipelines can require massive amounts of compute power. This means a lot of energy is used to process and transfer data at scale. So, understanding these factors is crucial for making our software more energy efficient. It's about making smarter choices to reduce unnecessary energy consumption across all these areas. Let's talk about why energy-efficient applications truly matter. First, there's the environmental impact. Software actually drives hardware, and as you know, hardware consumes energy. So, when we develop more efficient apps, we're helping to reduce the carbon footprint across billions of devices and data centers worldwide. Next, there's the user experience. Optimized code leads to longer battery life, faster performance, and devices that stay cooler. Imagine lightweight apps that don't drain your phone's battery. That's a win for users and developers alike. Then we have cost savings. Using less energy means lower cloud bills, fewer hardware upgrades, and a leaner, more sustainable infrastructure overall. And finally, regulatory readiness is becoming more important. Designing energy-aware applications aligns with sustainability goals and helps us stay ahead of emerging green technology regulations. All these points connect back to our overall theme, creating smarter, greener, and more efficient technology solutions for the future. Let's explore the principles of green coding and see how we can make our software more sustainable. First, efficient algorithms are crucial. This means choosing logic that minimizes both CPU cycles and memory usage, which directly leads to less energy consumption per computation. Next, minimizing resource usage involves avoiding unnecessary input-output operations, network calls, and background tasks. Think about techniques like lazy loading, caching, and batching to reduce the workload on the system. Another key point is optimizing for hardware. Tailoring your code to run efficiently on the specific devices you're targeting, especially mobile and edge hardware, can make a significant difference. For example, using quantized models for low-power inference helps achieve better performance with less energy. Reducing redundancy is also vital. This means eliminating duplicate computations, unused libraries, and bloated dependencies. The benefit? Smaller binaries that load faster and consume less energy. Monitoring and measuring energy consumption is another essential principle. Using profiling tools like Intel Power Gadget, Green Metrics Tool, or Carbon Tracker allows you to track how much energy your application uses and identify areas for improvement. Finally, designing for longevity involves writing maintainable and modular code. When your code is well structured, it's easier to update and avoid frequent rewrites, which helps reduce unnecessary reprocessing and waste. Together, these principles help us develop software that's not only efficient, but also environmentally responsible, aligning with the larger goal of sustainable technology. Now, let's dive into optimizing algorithms for efficiency. First, it's crucial to choose the right algorithm. Using time and space-efficient approaches, like quicksort instead of bubble sort, can make a big difference. The impact: faster execution and lower power consumption. Next, reducing complexity is key. Strive for lower big O time and space complexities, for example, replacing nested loops with hash maps or pre-computed lookups to streamline your code. Third, avoid redundant computation by caching results, reusing data, and eliminating unnecessary recalculations. Think of memoization in dynamic programming. It's a powerful technique to save time. Fourth, profiling and benchmarking are essential. Use tools like cprofile in Python, perf on Linux, or Intel vTune to identify performance bottlenecks. Finally, tailor your algorithms to the hardware you're targeting. Optimize for specific devices with techniques like vectorization, parallelism, or quantization where appropriate. Connecting all these points, the overall goal is to make your algorithms not just correct, but as efficient as possible for the environment they run in. Let's talk about reducing resource consumption, which is crucial for optimizing our systems. First, minimizing I/O operations is key. That means avoiding unnecessary disk reads and writes, as well as network calls. A good tip here is to batch requests together, use caching effectively, and implement lazy loading so we only load what we need when we need it. Next, optimizing memory usage can make a big difference. We want to free unused objects, prevent memory leaks, and choose efficient data structures. For example, using sets instead of lists for lookups can significantly improve performance because sets offer faster search times. The third point is about reducing CPU load. We should focus on using efficient algorithms, avoiding busy wait loops that waste cycles, and parallelizing tasks where appropriate. The benefit: fewer CPU cycles used, which means lower power consumption and better overall efficiency. Then, trimming dependencies is an often overlooked but impactful step. Removing unused libraries and bloated packages results in smaller builds and faster startup times, making our applications leaner and more responsive. Finally, profiling and monitoring are essential. Using tools like the Green Metrics tool, Intel Power Gadget, or perf allows us to track resource usage and identify bottlenecks. This way, we can make data-driven improvements and ensure our systems run as efficiently as possible. All these strategies connect back to our overall goal of building more sustainable, efficient, and high-performing systems that meet modern demands. Let's talk about efficient data management, which is crucial for handling large datasets effectively. First, choosing the right data structures is key. For example, dictionaries are great for fast lookups, while generators are ideal for streaming data without loading everything into memory at once. This choice directly impacts memory usage and access speed. Next, we want to avoid redundant storage and data transfers. That means not duplicating data unnecessarily and minimizing operations like serialization and deserialization, which can be costly. Smart techniques like compressing data, batching transfers, and caching results can make a big difference in performance. Processing large data in chunks is another vital strategy. Instead of loading entire files, we can process them piece by piece. For instance, using pandas, read CSV with a chunk size parameter allows us to handle big files efficiently without overwhelming memory. Filtering and cleaning data early in the pipeline is also highly effective. By removing irrelevant or erroneous data up front, we reduce the volume we need to process later on. This not only saves computational resources, but also enhances the accuracy of our analysis. Finally, monitoring and profiling our data pipeline helps us identify bottlenecks and optimize resource usage. Tools like Apache Spark UI, Dask dashboards, and memory profilers provide valuable insights into how our data flows and where improvements can be made. Overall, These strategies form the backbone of managing data efficiently, ensuring our workflows are fast, reliable, and scalable. Let's talk about building energy-efficient AI models. First, choosing lightweight architectures is essential. Using smaller models like MobileNet or Distill-BERT can really speed up inference and reduce power consumption, making them perfect for resource-constrained environments. Next, quantization and pruning are powerful techniques. By reducing the precision of calculations, like moving from float 32 to int8, we shrink the model size. Pruning removes redundant weights, which not only cuts down on storage but also speeds up computation. Optimizing training processes also plays a key role. Using efficient optimizers, implementing early stopping, and leveraging mixed precision training help reduce GPU hours and energy use without sacrificing model quality. When it comes to deployment, smart strategies matter. Running inference on edge devices whenever possible minimizes the need for constant cloud communication, saving energy. Batching predictions in the cloud can further optimize resource use and reduce idle compute time. Finally, continuous monitoring is crucial. Tracking energy consumption and model performance over time allows us to make informed decisions. We only retrain when necessary, ensuring our models stay efficient and effective without unnecessary energy expenditure. All these steps connect back to our overall goal: creating AI solutions that are not just powerful, but also sustainable and mindful of energy use. Let's now explore some essential tools and techniques for making AI development more sustainable. First up is profiling and monitoring. This involves tracking energy use, CPU and GPU loads, as well as memory consumption during your model training and inference. By doing this, you can identify bottlenecks and optimize resource usage effectively. Some great tools for this purpose include Intel Power Gadget, Green Metrics Tool, Code Carbon, and Carbon Tracker. Next, we have algorithm and code optimization. The goal here is to make your code more efficient by using better data structures, reducing computational complexity, and avoiding unnecessary calculations. Techniques like memoization, lazy loading, vectorization, and pruning can significantly speed things up and lower energy consumption. Moving on to lightweight model design. Building smaller, faster AI models is crucial for deployment at the edge, where resources are limited. Tools like MobileNet, Distill-BERT, ONNX, and TensorRT help create these compact models. Techniques such as quantization, pruning, and mixed precision training further reduce model size and improve speed without sacrificing too much accuracy. Then there's efficient data handling. Streamlining how you manage data by streaming, batching, and filtering early helps cut down on input-output operations and memory load. Tools like Dask, Pandas with chunk size, and Apache Arrow are invaluable for handling large datasets efficiently. Finally, sustainable deployment focuses on managing your models in production. Using orchestration platforms like Kubernetes, Airflow, MLflow, and Docker allows you to control updates, scale intelligently, and minimize idle compute resources, all contributing to a more sustainable operation. Connecting all these points, it's clear that combining the right tools and techniques can make a significant difference in reducing the environmental impact of AI, aligning perfectly with our overall goal of responsible AI development. Let's wrap up with a quick summary of why energy efficiency truly matters. The decisions we make around software have a direct impact on energy consumption, system performance, and sustainability. By choosing efficient algorithms, optimizing data handling, and deploying thoughtfully, we can significantly reduce resource use. Emerging technologies like edge AI, federated learning, and hybrid architectures allow us to create low-latency, privacy-safe solutions, crucial for modern applications. Tools such as MLflow, Docker, and Code Carbon are invaluable for monitoring, optimizing, and scaling responsibly, ensuring our systems are both efficient and sustainable. Remember, green coding isn't just about doing the right thing. It's essential to building future-proof, regulation-compliant systems that stand the test of time. Now, for the call to action, build with purpose. Start by profiling your code to identify bottlenecks. Opt for lightweight models whenever possible. Streamline your data pipelines to eliminate waste. And always design with longevity and impact in mind. And as I like to say, every watt saved is a step towards sustainable innovation. Let's connect with Talent Bridge to stay updated and engaged. You can visit our website at talentbridge.com, where you'll find all the resources and information about our programs. We're also active on social media, so be sure to follow us on LinkedIn at /@talentbridgeodu, Instagram at /@businessandcareerin, YouTube at @talentbridgeodu, and Medium at @talentbridge. These platforms are great ways to stay in touch, get the latest news, and access helpful content. Remember, engaging with us online is a key part of building your professional network and advancing your career. So, I encourage you to connect with us through these channels and continue the conversation beyond this presentation. Thank you for your attention, and we look forward to engaging with you on these platforms.